This is the second part of the 3-session series on projectile motion. We talked about the basics of 1D projectile motion in the first session. If you haven't seen it, you can find its link below. In session 2 here, we will discuss the 2D basics, and later in the third session, we will cover some interesting and challenging projectile motion problems. So let's get started. A quick review of X and Y components in the 2D space. When we have a vector, it would have magnitude and direction, which is defined by an angle theta. This can be any vector, and we are using velocity v in our example. The velocity vector can then be broken down into an x component, v sub x, equaling velocity magnitude v times cosine of the angle theta, and the y component, v sub y, is v times sine theta. Likewise, we can see similar expressions for acceleration. This is fairly basic definition. And if you'd like to see more about it, you can always search up the term vector in physics for more information. A quick review of the 1D projectile motion here. Governed by these two fundamental equations. You can learn more about 1D projectile motion in session 1 by following the link below. In the 2D space, we define the horizontal direction as x, and the vertical direction y, perpendicular to the Earth's surface. When a projectile is thrown out, it travels up and down, as well as in the horizontal x direction. And we would like to understand its velocity and position terms. Rearrange a bit here, keeping the equations for reference later. And for 2D, the vertical component of the initial velocity, v sub 0 y, is v sub 0 times sine theta. Recall our assumptions, also listed in the upper right corner. We only have gravity acting in the vertical direction. So we have v sub y, the y component of the velocity, equals v sub 0, or the initial velocity, times sine theta minus g times t. Note this is following exactly the 1D equation up there, with substituting in the y component of the initial velocity. The vertical position, y, is the initial y position, plus v sub 0 times sine theta times t, and minus 1/2 of g times t squared. Here's the new portion in 2D. The projectile also travels in the horizontal x direction. We have the horizontal component of the initial velocity, v sub 0x, equal to v sub 0 times cosine theta. Since there's no air resistance or any external force in the horizontal direction, the velocity in the x direction, v sub x, remains constant and equal to the initial velocity v sub 0x, and the x position is then the initial position plus velocity in x multiplied by time t. There we have it. These are the fundamental governing equations of 2D projectile motion. Again, they are under the assumption that there's no air resistance, and gravity is constant. Okay, let's now take a look at a cannonball fired from the ground level with a certain speed and at a certain angle. Let's throw in some numbers. Say the initial speed is 100 meters per second and the angle theta is 60 degrees from the ground. The initial components at t equal to 0 seconds are 86.6 meters per second in the vertical y direction and 50 meters per second in the horizontal x direction. Make sense? Right. Using the four equations above, we can then determine velocity and position at any given time. As an example, let's try t of 2 seconds. For the y direction velocity, v sub y, at t of 2 seconds, we have the initial y direction velocity, 86.6 meters per second, minus 10 meters per second squared times 2 seconds. This comes to 66.6 meters per second. Note that we use an approximation of 10 meters per second squared for g, just to simplify the math a bit. The horizontal x direction velocity, v sub x, stays constant at 50 meters per second, because there's no air resistance. Likewise, we can solve for x and y position by using the two position equations above and get 153.2 meters for y and 100 meters for x, at t of 2 seconds. Repeating this exercise for different time, t, we can fill a table like this. We also see the maximum height, y submax, is 375 meters, and the maximum range, x submax, is 870 meters. Now, let's think about this problem a bit more. If I increase the angle theta, I will get more vertical velocity, and the cannonball will travel in air longer. But I will also have a smaller horizontal velocity, and likely not that great a range. If I reduce the angle theta, I will get a lot of horizontal velocity, but not so much of the vertical velocity, as well as not so much the traveling time. So what is the optimal angle theta that would give me the maximum range, or longest horizontal distance? We know the total traveling time is v sub 0 times sine theta divided by gravity g. This is derived from the first vertical velocity equation at the top. And we want to maximize the horizontal distance, which is v sub 0 times cosine theta times t, based on the horizontal position equation at the top. Substitute time t into the horizontal distance, which then becomes v sub 0 squared over g times sine theta times cosine theta. We know v sub 0 squared over g is a constant. Therefore, this problem of finding maximum horizontal distance can be simplified to maximizing sine theta times cosine theta. Finding the maximum of this product of sine theta and cosine theta is a solvable problem and is straightforward. It will require some basic calculus, essentially setting its derivative to 0, at which point, the product term does not change much, and we call it is at its extremum, meaning it is at either its maximum or minimum value. By further confirming its second derivative is less than 0, we then know it is a maximum. I will not bore you with the details in the calculus derivation. They are listed here, and you can go through them step by step if you are interested, just to double check. The bottom line is that the optimal angle is 45 degrees for the cannonball to achieve the maximum range. Very nice. Let's next do an interesting problem of targeting practice. Suppose I place the cannon on a hill that is 100 meters above the ground where my target is. This cannon has the same muzzle speed of 100 meters per second, the only knob I have is the angle theta. And I want to know what theta to use to hit my target 1000 horizontal meters away on the ground. Here's a graphic representation of the problem. I got my cannon 100 meters above the ground on a hill. My target is 1000 meters away. And we want to know what theta to use. Let's throw in some numbers into first the vertical position equation, and then the horizontal position equation. Both equations are listed at the top. This is an example problem where all the position information is known, and we want to know what angle to use for the cannon. Simplify the two equations a bit. We have two equations and two variables, t and theta. We can substitute t into the first equation, and have this rather funny-looking equation for a single variable theta. Honestly, I am not sure if there is an analytical solution to this equation. Maybe, maybe not. Looking quite complicated trigonometry to me. What I know for certain is that we can solve it numerically. There are lots of different software out there, capable of solving this problem numerically. I just used Excel to obtain the solutions. There are actually two thetas we can use, 28.93 degrees or 55.36 degrees. Either one would hit the target, but the time it takes is a bit different. The 28.93 degree one takes about 11.43 seconds, and the 55.36 degree one takes a bit longer, about 17.59 seconds. That's it for this session. Thanks for staying with me to the end. Should I include a short clip here on how I run Excel for the numerical solutions? Let me see what I can do. Here's my Excel. I paste in the equation we would like to solve, just as a reference we can look at. I first have an input variable for the angle theta, and then a function equaling the left side of the equation. We can type in an arbitrary angle value between 0 and 90 degrees, this is what we want to solve for later. For now, I just type in 20 degrees. Next, we type in the left side of the equation and treat it as a function. Since our angle is in degrees, and my Excel is set to take angles in radians, we need to do a conversion from degree to radian. 180 degree is pi in radian. We obtain a value for this function. We know if we have a certain angle theta such that this function becomes 0, that certain theta is a solution to our equation. This is where the goal seek excel function can do. We go to data. And you will then see a what if analysis button, under which there's a goal seek function. Click on it, a small window pops up. You want to have the set cell set to the function formula cell, which is cell C6, the to value set to 0, because we would like to see the left side of the equation equals 0. The by changing cell is asking which one is the input variable. That would be theta in our case, so we set to cell B6. Click on OK, you will see Excel goes through some iteration, and gives out an angle of 28.93 degrees where the function gets very close to 0. So we have our first solution of 28.93 degrees. We can also type in a different angle, starting value. This time we go with an angle greater than 45 degrees, say 60 degrees. The starting value is not that important, as the goal seek function will find the final solution for you. Repeat the same goal seek process, and we have the second solution of 55.35 or 6 degrees. How do we know there are two solutions? One is that there's a squared term in the equation, and we can also think of this as following. We know the optimal angle to achieve maximum range is 45 degrees. All other angles, either greater than or less than 45 degrees, would give us a shorter range. Therefore, there must be a solution that is less than 45 degrees, and another solution that is greater than 45 degrees. That's all for now. And if you like what you see, please hit the like button, subscribe, and share. Thank you.